All right, ladies and gentlemen, today we're going to be going over Graham's law, so another law, gas law we can add to our bag of tricks. Before we do that, we're going to go over an application of Dalton's law that we didn't discuss. So we have our case where we're doing a collection of gas over water at a given temperature. We have that general equation. Our total pressure is equal to the partial pressures of A plus the partial pressure of B. In this case, our total pressure is going to be barometric pressure. Our partial pressure A is going to be what we're solving for, and the partial pressure of B is going to be our partial pressure of water vapor. So we'll do this question together in class. So calculate the partial pressure of hydrogen gas collected over water if the temperature is 303 Kelvin and the barometric pressure is 182.5 millimeters mercury. So moving into Graham's law. Graham's law states the rate at which a gas goes from a high concentration to a low concentration is inversely proportionate to the square root of its formula mass or its density. So we have our formulas here. So rate of A over rate of B is equal to the square root of molar mass of B over molar mass of A, or the square root of density of B over density of A. Do this problem together here. Determine the rate of diffusion of a gas with a density of 2.121 grams per liter compared to a gas with a density of 1.184 grams per liter. So we write down rate of A over rate of B equals, in this case, we know we're gonna do the square root. We're given densities. So we have density of B over density of A. We're gonna shorthand this a little bit. So RA over RB is equal to the square root of DB over DA. So write down what we know. We have that square root. First gas that we run into in our problem is 2.121 grams per liter. That's density A, so that goes on the bottom. On the top, we're going to do 1.184 grams per liter. Solve for that. Following sig figs, so we have 0.7471 is our answer. Notice there's no units, those cancel out, so we're just comparing those. So how do we know what our answer is here? R of A over R of B. If it's greater than 1, gas A diffuses faster. If RA over RB is less than 1, it diffuses slower. In our case, it's less than 1. So gas A is 0.7471 times as fast as gas B. So gas A is slower. That is our answer. We're going to go over this one together in class. Determine the rate of effusion of nitrogen gas compared to oxygen gas. And we're going to go over what is the density of a gas that diffuses 0.8521 times as fast as a gas with a density of 76.32 grams per milliliter. We'll do this one with a partner. Compare the rates of diffusion of a gas with a density of 12.95 grams per milliliter to a gas with a density of 5.298 grams per milliliter. We'll see you in class. Have a good one.